So one of the things, clear back in Unit 1, we kind of talked about how things are organized. And we said, of course, we're on the Earth, and the Earth is a planet that orbits the sun. Our sun is just a star, and our sun is a star that's a member of the Milky Way galaxy. And we really can't see the Milky Way galaxy because we're in it. I brought a prop here today, and this is actually going to be my Milky Way galaxy. So one of the things we know is that I'll put BH, there's a black hole kind of in the center, and we'll be talking more about that. There's 4 major spiral arms and a few little segments. Okay, so that's my black hole, or that's not black hole. This is my Milky Way galaxy. And actually the sun is about halfway from the black hole in the center. I'll put, this will be my sun. I gotta be careful because this is a permanent marker. Do not mark on the whiteboard, it's a permanent marker. Okay. So when we're looking at the Milky Way, okay, this could be, so there's the sun, okay, we're kind of looking at the edge. Does that make sense? So this is the Milky Way in the sky, and we're kind of looking into the disk of our galaxy. Just gorgeous. My goodness gracious. So, and you can make this statement about all science. And then one of the cool things about science is, well, everybody has an ego. We all have self, how cool we think we are, and all that. But I think when it comes to science, we kind of let science speak for itself. And we're not afraid to bring in new information and consider new things. So things are evolving, what we know. And along those lines, and I thought I'd kind of write this up here, I am amazed at this one little piece of history with regard to astronomy. Now, a lot of times little kids will have a sense of this. You know, this is the Milky Way galaxy. Like, I kind of got that. But the story I'm going to tell you was, got right to the chase, 1926 was not that long ago. Of course, I was born after 1926. But 1926 was the only time when we finally figured out that here's one galaxy here, and I should have brought extra plates. Here's a galaxy over here, here's a galaxy over here. It wasn't until 1926 we understood the concept of a galaxy. So instead of that concept of a galaxy, folks back then, I'll kind of do a, let's see, I don't know how I want to draw this. Some of us saw the Andromeda galaxy, and it looks kind of like this fuzzy sort of thing. Kind of has some structure, okay? This is my Andromeda galaxy. And people would look at that and they're like, well, that just looks like a nebula. And I'll put in parentheses that we know it's Andromeda galaxy. And one of the many cool things about astronomy, and they do like documentaries about this, is that galaxy actually is intersecting, doing a dance with this galaxy. So if I had 2 plates, actually, I could kind of show them kind of coming together. And that's going to happen. But anyway, back in 1755, folks were like, so I see that, is it like another plate, another galaxy, or is it just like a star that kind of left its material, a nebula? All right, so that was 1755. I'll put a question mark. Okay, so in 1845, you're going to see some pictures. We have Lord Rosse, bless his heart, an enthusiast, actually was looking at nebula. And these nebula, and this is what he actually drew. He used this telescope to draw this picture. Okay, now we can't see the Milky Way galaxy, but that's another galaxy up there. That's the Whirlpool galaxy, okay? So that is an awesome another, what we call face-on galaxy. Didn't know if it was a nebula, didn't know if it was its own little galaxy. That's M51, not bad. So there's his sketch, there's the photograph. I'm like, that's awesome. So, and actually, does it kind of look like there might be 2 galaxies here? It does to me. Galaxies a lot of times do this sort of dance, and I think if I'm remembering this right, there is an interaction between these 2, a big galaxy and a little galaxy. So that was 1845. People still scratching their head. So 1920, I told you 1926 was our aha, okay? 1920, actually, there was this debate, and it was between Shapley and Curtis. And I can never remember who was on which side. But 1920, they basically get together and they kick things around as scientists do. Okay, and then my caption here is, unfortunately, it debated much heat, or generated much heat, but shed little light. And like the slide says, the missing piece is, how far is that nebula? Well, earlier work by a woman, no doubt, actually, I think it was 1923. Oh, maybe it's 23, 26. Henrietta Leavitt had actually earlier, this is so cool, let me see if I can get a different color. She did work where I'm going to put a little star here, and that's going to be our RR Lyre, a special sort of star called an RR Lyre star. When we did the HR diagrams a while back, remember, this is my HR diagram, here's my main sequence. These guys are giants or red giants. If a star gets up here in this area, sometimes it wiggles around a little bit. It wiggles around a little bit with regard to its luminosity. And actually, those HHR Lyres, they are wiggling around right here. And how much they wiggle around, how much they kind of they ebb and flow, get bright and dim, that's an indication of how bright they are. And if you can figure out how really bright they are, you can compare how really bright they are, their absolute magnitude with how bright they look, and you're like, dude, they're this dim, I know they're really supposed to be this bright if I were to visit them. So you're like, I know how far away that is. Bottom line. Okay? So that's it. That was it. The missing piece was distance. I'll put aha, and I've changed that to 1923 instead of 26, and I'll put distance, solved. I just think that is so cool. And 1923, 26 wasn't that long ago. So then, of course, like we do as scientists, we're like, dude, I am so going to apply that same technique to all sorts of different things. So this figure down here at the bottom, okay, this is of Messier, M stands for Messier, object number 100. So this Messier object 100 is, you can kind of see here, the center of the galaxy. These are the kind of the material of the disk of the galaxy. And I'm just amazed that people can actually, like right here, you're like, dude, you must have the coolest telescope ever, because they're kind of pointing at the variable star. And I'm not sure, these three boxes are trying to show you how the star is varying. I do not have the patience. But that was important for us to understand the concept of a galaxy. I just think that is so cool. So when we talk about galaxies being their own little island universe, that's what we mean, instead of just being like a nebula in our own galaxy. All right. And actually I'm kind of going back before the concept, or actually this is back to just our own Milky Way galaxy. One of the things, if you're a scientist, you're like, okay, I kind of got this sort of plane sort of thing going on with our galaxy, but where's the center? Well, actually, one of the things that work that was done early on, you can see the late 1700s, was this idea of looking for the center. And incorrectly, he tried, so this is Herschel, this is the dude with the cool telescope. What he tried to do was say, he's basically going to go out to the nighttime sky, and he's like, I'm going to go ahead and see where the center of brightness is. And and when he did that, he's like, oh, the center of brightness is here. So the center of our galaxy is here. The problem is that things are, we all know this, that as things get farther from us, they get dim. So it was wrong. He tried. Okay, he tried. So, oh, you guys, I didn't pass these out. So instead of that, sorry guys, instead of that, what he did, or what somebody did, was to look for these clusters of stars. We talked about there's two types of clusters of stars. There's open clusters and globular clusters. And some semesters I've made it an exam question when I did this semester because it just didn't make sense. My favorite type of cluster is a globular cluster. And some of you, I think, saw open clusters you probably like. But anyway, so instead what they did was to look for globular clusters. And we'll be talking more about kind of the Milky Way galaxy and a BH, black hole in the center. But, and maybe you can kind of think of it as in terms of being, because, so you can do your phones, but you can't talk. You can surf all you want, but you can't talk. Unless it's to me, unless, you know, which that works. But what they did was, and this would be a group effort, scientists work well together, is they found kind of hovering here and hovering here, globular clusters that were outside the plane of our galaxy. And they're like, dude, globular clusters and globular clusters. And it's almost a gravity thing. Globular clusters have mass. Black hole is a great sort of gravity attractor. Although black holes are not a cosmic vacuum cleaner. They don't go for spinning up things. Okay? And as it turns out, that's how it works. There are a bunch of globular clusters that actually kind of escort outside of the plane of our galaxy. So globular clusters, globular clusters. And if you figure we're here, we can see globular clusters. So it all works. That star that I said, the RR Lyre variable star, the one that's up here on an HR diagram, kind of wiggling back and forth, those were used to actually kind of pinpoint location, triangulate location. So that's pretty cool, I think. So, so again, the globular clusters are identifying the center of our galaxy. Here are a couple of globular clusters. And this is this. You might be like, well, how can you get this picture if you're actually here? But we can. Yeah, we've talked about different types of astronomy, and this is the type of astronomy that's not looking at visible light. This is looking at infrared light. Okay? So there actually would be the heart of our galaxy. So it's hard to map something that you're in the middle of. So one of the things we do is to kind of look at other galaxies and get a sense for what other galaxies are like and think, well, if they're like that, we're probably like that too. Another thing is to kind of tease the information coming from within our galaxy, different wavelengths. So like the slide says, we can actually, we can find these kind of pockets of gas in our own galaxy if we dial our observation to radio waves, infrared, X-ray, and gamma rays, not just visible light. Okay, so this is looking to other galaxies for clues. So for instance, this actually is Messier Object 83, M83. It's kind of a face-on galaxy. You can see it doesn't have like a bunch of spiral arms. It actually has kind of, it's a barred spiral. So we'll talk more about different types of spiral galaxies. But it has like one major spiral, or pair of spiral arms, okay? This is what it looks like in visible light, and this is what it looks like using radio waves, specifically a wavelength of 21 centimeters. So this is actually how we can map within the Milky Way galaxy to know things. This is specifically for, I believe, carbon monoxide, and it kind of shows you where the stuff is, and you need to have stuff in order for stars to be born. In other words, where this is we can have new stars born. When it talks about OB associations, you may not know what the word association means, but on your last unit exam, down here, when you guys, if you did the HR diagram, you put the OB, find, I, kiss me. OB are the hottest stars. So the hottest stars are kind of what we're looking for to kind of help birth other stars. So this obviously has to be a figure. So this would be our Milky Way galaxy. This is this. So our Milky Way galaxy, we used to think it was nice how I've drawn it, but instead I'm going to kind of modify this. We think that two of the major spiral arms actually kind of connect with the middle, and so it makes it more of like what we call a barred spiral. So that's kind of what's being shown up there. And it's hard to see that, but the caption says that actually, well, I'll say in a minute. The names of the spiral arms. This is what I thought it was. What I think might be an interesting question to put on the test is, where are we with regard to these spiral arms? We are on a short segment called the Orion arm, and actually I'm going to show you a figure here in a minute, what those arms look like together. So we're on the Orion arm, and we have the Sagittarius arm and the Perseus arm on either side of us. So I kind of drew this wrong. See, I'll take red. So this would be better if I put us kind of right there. We're on a short arm between the Sagittarius and the Perseus arm. Go Orion. So this again, we're kind of deducing where we are, but this again is our home. This is the Milky Way galaxy. You can see the barred spiral. You can see I like this slide because it kind of gives us a little bit of distances. Let's see, one distance I'm missing. It says we're about 26,000 light years from the center, so it's actually showing you, this is the edge on view, this is the face on view. These little dots right here are the globular clusters. So we're about halfway, which I wish it said 100,000 light years, but it doesn't. But if you add this, if you go from this edge to that edge, you're talking 100,000 light years. We're about 2,000 light years thick, about where we are. So, cool. So, I have some slides now to kind of show you how chaotic it is there. And actually, I'm going to show you a video, okay? But a black hole, you're like, dude, it's black. Why would I see anything like this glowing? Well, first off, this glowing actually was taken in infrared, okay? A few things about this slide before I forget. The location of this black hole actually is in the constellation Sagittarius. So I think seems like forever ago, we actually, while we were out, saw the asterism, the teapot. I'm a little teapot, short and stout. Here's my handle, here's my spout. So actually, if you take the spout on the teapot, which is part of Sagittarius, right there where the steam would come out, that actually is the center of our galaxy. So it's a very busy place. So we call it Sagittarius A star is that. It's in the constellation Sagittarius, and A star is this crazy looking object that must be a black hole. All right. So back to our kind of galaxy. This is a weird sort of looking thing. This would be, I'd hold my galaxy like this. Okay, that blue right there is what we call our nuclear bulge, kind of where the black hole is home to. This is the disk of our galaxy. This kind of creepy looking glowing thing, kind of looks like a celestial sphere. That actually is what we call the halo region of our galaxy. Okay. So one of the things, and actually I think this is looking at another galaxy, not our own galaxy, but our galaxy is like this too. Stars have to keep moving. If stars don't move, guess what? Gravity's going to make them pull into the center of the object that's kind of keeping them together. So our stars are moving, and I kind of have some kind of velocities coming up. So the sun has to be moving, and I'm not sure if it's clockwise or counterclockwise, but the star is orbiting the black hole. Now, our star is a disk star versus opposite of a disk star is a halo star. A lot of the stars that we love in the nighttime sky are halo stars. they actually move differently. So what you're seeing here is this red line is kind of the way the disk star moves, the way our sun would move. This is a different galaxy, but our sun would move like this. And you can kind of see the red, it's kind of bobs up and down, in and out of the plane of our galaxy. So that's kind of what's going on. It's amazing, and I've heard people say they're amazed too. If you figure there's our sun, and our cute little Earth is orbiting the sun as the sun moves. But as I understand it, actually our orbit of the sun is kind of like this. So we're orbiting the sun, and the sun is orbiting the black hole. So we kind of have an orderly motion, and so do all the stars in the disk. But the other stars, the halo stars, are your wild children. They go like this, and they go like this, and they go like this, okay? So they kind of have some more chaotic too, chaosness, if that's right. This is trying to show you kind of the nice orderly motion of the stars in the disk. That's this first one, the galactic plane, how they orbit the black hole, versus these guys. Don't they look like wild children? Okay, so these were the paths of the halo stars as they orbit the center of our galaxy, or any galaxy. Okay, so the Milky Way has a disk part to it. It has what we call a nuclear bulge, what's home to the black hole. It has a halo region. So I need to talk a little more about the halo region of our galaxy. We know that they first found it by kind of identifying globular clusters, like kind of buzzing around an object. The thing is that, well, what else is in our galaxy? So we have, in our halo, excuse me. So we have these globular clusters in the halo region. Another thing we have is not necessarily Andromeda galaxy, but we have a cute little dwarf, Sagittarius dwarf galaxy that is actually orbiting in our halo region. And like this slide says, that this actually, if my finger right here is the Sagittarius dwarf galaxy, when it moves through the plane of our galaxy, it leaves some stars. So it's like losing itself little by little, kind of being absorbed. It's called cannibalism, actually, in the lives of a big galaxy like the Milky Way and a cute little dwarf galaxy. Okay. So this is kind of showing you how our stars paths that our stars would orbit the central black hole, right? I don't care much about this, but I do care about this. So this is showing you how stars would orbit this would be disk stars, how they orbit the central black hole. So the red actually is kind of what we see, right? Now, one of the things that Kepler did, goodness, was this his third law? Kepler's third law of planetary motion said that when you get out to Jupiter, you slow down. So there's the sun. I didn't move the chair over there, but there's the sun. You get out to Neptune, you slow down. Okay? When you get out to stuff in the Kuiper Belt, it just moves more slowly. Why? Because it's farther from the thing that's making them move, which is the sun. So we would expect, actually, this blue line, that's kind of the decay of how fast things are moving. So the blue line, and I know I'm kind of switching gears between our galaxy and our solar system, but the blue line is what we would expect the motion of the stars to be. The red line, so exciting, the red line is what we observed it to be. So in other words, if you're way out far, this is farther from the center of our galaxy. If you're far from the center of our galaxy, you're going a heck of a lot faster than you really ought to be. Well, there's an explanation for that. And the explanation for that actually kind of steps into something else that we'll need to talk about when we talk about just our universe. There's this thing called dark matter. Dark meaning you don't see it. So you're like, it could be, well, it just doesn't glow. Well, that's true. Some of the dark matter could be brown dwarfs or stars that used to be and stopped shining. That could be dark matter. But that's normal matter, but you can't make up, how do I say this? the numbers don't crunch, so that there has to be actually some even more exotic things that are dark matter. Back to the problem with kind of why these things go so fast. Well, if you put dark matter, distribute dark matter, we can't see it, but it's not dark matter, in our halo region, then you can get back to the orbit curve that we observed. Okay? So what is dark matter? Well, it could be, like I said, it could be black holes, it could be just gas that's not shiny, it could be Jupiter-like objects, you know, the star wannabes kind of, failed stars, brown dwarfs, or something more exotic. Again, then we're kind of getting into what Unit 5 is going to be, just touch on that Wednesday week after you take your test. This slide is the same information, somewhat redundant. Again, so what you're looking at is the blue line is actually what we observed, okay? This red line is what we thought, if you get far enough away from the center of our galaxy, this is how slow you should be going. This is how fast it was observed. And that has to do with the dark matter in the halo of our galaxy. Okay. So, how fast are we going? Well, we are going, when I say we, I don't mean the planet Earth. Well, sort of, because the Earth is tagging along with the Sun, and the Sun is orbiting the center of our galaxy at 230 kilometers per second. But remember, we said the way that works, as long as you're going at a constant speed, you don't, it's like in an elevator. You feel that initial, oh, and you feel the later, oh, but in between on an elevator, like, as long as you're going constant speed, it all works. So what that means, since we're going that speed, is that it takes our Sun, I think this is so exciting, 230 million years to make one trip around the galaxy. That is so cool. So what that looks like then is that the last time that the Sun was where it is now, the Earth was actually home to the early stages of dinosaurs. So, I think I'm okay for, got 2 minutes. Okay, we'll leave this, we'll kind of springboard off of this for tomorrow, or, not tomorrow, but when we meet again, there's a good chance we're going to meet in that classroom, so we can do a few more slides. So we'll pick up here. Could you get this? Thank you. So we'll keep doing what we've been doing, where if you want to get extra credit, you can turn these in before you come take your test on December 10th. Otherwise, turn it on December 10th. All right.